that, all right, my name is Signell. I've been using Xarray for a while. This is the original vintage Xarray t-shirts. I think they got a new logo now. In fact, I was using Xarray back when it was called Xray, so it's quite a while. But I'm not an Xarray developer. I'm just a user. So I don't know everything about Xarray, but I'll tell you about my little world, the way I use Xarray. But I'm going to do it through the standard Python, the Xarray tutorial, Xarray in 45 minutes. Xarray in 45 minutes, actually the tutorial takes more like an hour and a half. So we're only going to hit parts of that tutorial. And then I'm going to show you a sort of like a more advanced tutorial, which is also out, in the public, but it's going to hit some of these on these topics that Eli was kind of mentioning about accessing data directly from these public data sets that the cloud providers have, and that other people, many institutions are starting to share their big data files through these object storage on the cloud storage. And so I'm going to give an Xarray tutorial today, but I just want to put this one slide up that I've been very heavily involved with this very cool project called Pangeo. And it sort of uses Xarray as the core package behind this kind of typical workflow where inside that box in the middle is like a Jupyter hub, like the one we're using today. And we're using Xarray on that hub. And we typically use Holoviz to visualize the data. So you saw plot earlier, and that's really cool. And then there's also something called HP plot that you can do with Xarray that gives you interactive exploration of the data, so which is also super cool and sometimes critical if you're dealing with super high resolution model output. So those two packages access data through, it can access data in parallel in addition to the ways that you saw earlier today, like accessing OpenDAP and NetCDF files directly. You can use Dask to open those same files and data from object storage in parallel using Dask, which is a way to scale out computation. So if you have to process more than say maybe a gigabyte of data, you probably want to be doing it with Dask, which happens to be underneath the hood of Xarray. So I'll just jump into this. Actually, yeah. So that was my one slide, and now I'm going to just jump back to the hub. So we're going to look at this again. This is just a standard Xarray tutorial you can find out by just searching Xarray in 45 minutes. You'll get there probably on the first link. And okay. All right. So I mean, you've already heard something about Xarray in a lot of talks, and Xarray is, if you're working with data like gridded, any kind of gridded data, maybe has more. If it's not just tabular data, if it has additional dimensions, Xarray is the package you want to be using. And you'll hear actually a lot of people say, okay, if you're using tabular data, use pandas, and if you have more dimensions than that, use Xarray. But I usually tell people just use Xarray unless there's a good reason that you need to use pandas, because Xarray carries along attributes, has Dask built in, all these good things. So just to review though, this is kind of a little pictorial about what Xarray does. Is that one more? Sorry. So yeah, it's really the NetCDF data model represented in Python. So you have a data set. Inside the data set, you have data arrays. The data arrays are typically like variables, like in this case, we have temperature and precipitation as these two cubes of data, and they share latitude and longitude as coordinates. And then they both have time dimension. So this thing, the whole thing is a data set, as you can see on the bottom there. And then these data array actually is the data for the variable plus the coordinates. And so this is a little bit, I suppose, probably review at this point, considering what you've seen already, but maybe this is going to be, helpful. Now, I'm not sure, I usually recommend, don't try to just follow along in real time, because then you kind of lose track of what the presentation is, or at least so you might just like wait and try it afterwards, especially when we get to the next notebook. If you want to, I'm not going to stop, but I'm going to try it. So this, in this case, there's actually, this is a little bit obfuscates what's going on, but we load this data set called air temperature, and really what's going on behind the scenes is it's downloading a small netcdf file to your local computer, to the hub in this case, and then it's opening it up. And we've seen this before already. We have a data that says at the top, data set. It has dimensions, it has coordinates, as in this case, it only has one data variable. And you can see something over here in this nice little display. You can kind of see like, okay, the latitude is ticking down from 75 to 15, longitude's going from 200 to 330. The time expense. So you can tell sort of like pretty much off the bat, just looking at this, whether you got like open the data set you meant to load, you're meant to be loading. And these little buttons over here, if you click them, you can see the attributes. So, all these different attributes for this variable, like the units, degrees, Kelvin, and some other stuff. And if you click this little guy over on the right, it'll show you something about, why isn't that showing? I think because that's off the screen. Oh, it's showing. There we go. So it shows something about the array in this case. Actually, so this is something about the data, and this is about the attributes, essentially. Okay. Questions? Yeah, you can just yell out a question if as we go along here. Okay, so actually, if we just as I want, we can want to pop in a cell here and see. There's other things like DS, like encoding. There's these attributes that you can see.
Yeah. I'm zooming back in a little bit.
Oh yeah.
Thank you so much.
Yeah.
Perfect.
In this case, you can see that this actually is a netcdf file that was downloaded into this cache directory, blah, 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 blah. So we could, it is sitting here on disk. And actually, you can get, if we look at a particular variable like air temperature, we can see like that it's actually an integer 16 and its original shape and so on. So we get some more information about the variable in addition to just the attributes. Okay, so so here you have a data set, this object ds, and it's a dictionary, and you can access the variables as a dictionary item. So let's say just like ds air, and again it shows you now a data array. Okay, so this is one of the data arrays in this data set, and again they share all these different coordinates. You can also use this notation ds dot air, but I kind of usually recommend people use this approach just because it's a little more clear what's going on. Like, is this like just looking at this, you don't know whether this is a variable or it's an attribute, right? Like, so it's, in this case, it gives you back a data array, but if you type, some other attribute of this data set, will give you back that attribute. So it's, but in either case, actually, if you start typing like left bracket and something, and like if I start typing like A, and I can do tab and see a list. So like when you have like 300 variables, this can be pretty handy. You can remember the first letter, but then you can hit tab and it'll have a drop down, and then you can just select from this drop down. Oops, that didn't work. Okay, so a data array, as I mentioned, it can have, they can have these, both data sets and data arrays can have these attributes, arbitrary number of attributes. In this case, we're gonna look at something called name. If you do something like, something that doesn't exist, it comes back and tells you it doesn't exist. If you wanted to see all the attributes, you can do attrs and see, again, like that list that we saw when we clicked up above. So this is a dictionary. Okay. So you can add things to this dictionary, create your own attributes. We're gonna do that below. So what do these Xarray things have? They have named dimensions. So there's something called .dims, okay? So if we do da.dims, we can see it depends on time, lat, lon. Coordinate variables, you can type coords, you get back the names of these coordinates. And this is, I like to think of these as like, if you make a plot of the thing, what would the X label be and the Y label on your axis and your time axis? It would be these, you name it, lat, lon, and time. And in this case, latitude is a function of the dimension called lat. So, this is a net CDF kind of thing. But lon is a function of lon and time of time. So these are all one-dimensional variables. So in this case, latitude is one-dimensional, longitude is one-dimensional, time is one-dimensional. But they could be latitude and longitude could be two-dimensional or other things, and still be coordinates. Okay, and actually, Alex, or anybody else who knows more about Xarray, if I say something is wrong, please go. Excuse me, that is not quite right, Rich.
We'll use the buzzer.
Yeah. Okay. Whoa. Okay. So you can look at the coordinate values here, and if you want, again, because this is a dictionary, you could extract the coordinates this way. Okay, these are kind of straightforward. And here again, I already showed this, getting the whole list of attributes, and then making up an attribute. Who is awesome, Xarray, blue, and and now who's awesome, big one. So, all right, so Xarray has this, it's good for array data, and if you type on one of these things, if you type .data, you get back the data as a NumPy array, so it's underlying this thing. So a lot of people, before they use Xarray, they're used to using NumPy to work with these arrays of data. And I see this all the time. Somebody goes to like an Xarray tutorial and they learn something about Xarray, but then they can't figure out how to stay in Xarray. And they end up just going back to doing .data and working with the data, and doing loops and for loops and stuff. And because that's the way they learned how to do it in MATLAB or whatever. But you can almost never have to do that. You can almost always stay in Xarray, and I encourage you to please try to figure out how to stay in Xarray, because, well, we'll show you right now. If you treat these things as NumPy arrays, and if we do a type on this, we see in fact it is a NumPy array. What happens if you just grab the data like this? You can do this air.lat.data and ds.air.data, and now you've loaded all the data into memory. And but not only, so now you've got these NumPy arrays, but that then requires you, for one thing, to you've got all the data in memory, which if you've got a big data set, you don't really want. But also, now you're just back to indexing on these data arrays by using integers, right? Like 0, this is going to be 0, and colons, the whole thing, right? So I'm going to get one time slice of, what was the first index is time. Okay, right, you got to remember that, right? The first index is time, but it's not very clear, right? If this could be rearranged, NetCDF doesn't tell you that time has to be this dimension, it could be this other dimension. So what is this? You have to know what the order of the variables, the dimensions are, in order to pull out the right piece of data and use these integers. And this is what all we're used to before Xarray came along, and it kind of stunk, right? This is not cool. It works. You can extract your slice of time, your time slice. And you can do things like this again, and get the mean. That's cool. You can just type mean axis equals 1. But again, what did you just do? Yeah, it says you can't tell that they actually took a time, a dimension, a mean across the time dimension. Now with Xarray, it looks the same thing, but if you don't do dot data, you can, as we saw earlier in Colin's presentation, you can say I cell time equals 0. It's a lot more clear what you're doing, right? And then plot one. Okay, so we can do this I cell instead of using an index, and it's more clear what we're doing. We can also say dimension equals time instead of like whatever axis time is, right? So we don't have to figure it out. We can just say, and it's more clear, we say dimension equals time. So we're going to take the mean over dimension equals time and plot with x equals long, right? So that's just a lot more clear for one thing about what's going on. But even better than that is we can use these coordinates to actually, instead of doing I cell and specifying some index, like we can specify an actual time, right? So like now we have the data set again, okay? We have these coordinates, and these bold coordinates here mean so we can index along these coordinates using the actual coordinate values that we see over here. Okay, so we can select all of 2013 and all the data from May by doing 2013's -05. So if we type this, we can see now we have 124 values, okay? And of course, the full spatial extent again, which is very small because this is a test case, just an example, but that's how easy it is to pull out all the data for a particular time. And as was mentioned earlier, we haven't actually done the computation yet until we actually need the data. That's another cool thing about Xarray. You can kind of see what's going to happen before you actually load the data. If it's not what you actually meant to have happen, then you don't change it before you go pull down a whole bunch of data and oops, that's not what I wanted to do. So you can pull out a range by doing things like this. Okay, so instead of saying time equals a value, you can say slice and give it 2 values, a start and a stop, and it will find all the data between May 2013 and July 2013. Okay, so just doing that again. So now we get 368 time values, and again, we haven't read the data yet.
Real quick, for the slicing, is it inclusive or exclusive?
It's inclusive. Well, yeah, the data, you mean like the end values? Or?
Yeah.
Yeah, I guess the end values. Yeah. Is that what you meant?
Yeah, like for the end value, is it up to that point or does it include that?
Oh yeah, no, it includes the point. Yeah. So okay, so this is also showing that you can select, if you select for these one-dimensional coordinates, if you just put some values in here as a list, you can also just extract points at these certain long locations. So, but you need to do this method equals nearest for it to find the nearest point. If you don't, it'll say like I couldn't find any data at this, unless you got exactly the right coordinate value, it'll return an error. So if you use this method nearest though, you can come back and you see how you have this little 2x2 now data set where you've extracted the data at those locations. Okay, and you can still use this sort of I cell kind of thing, time equals 0. I mean, this still is kind of useful, right? I often use I cell time equals 0 just to pull the first data value. I don't want to worry about what time it is, right? I just want to see the first value or the last one, -1. We'll give you the last value. So again here, this gives you back. Yeah, so it's saying here this is much better than just going, ds air 0, 2, 3, these random indices without knowing what they are. Time equals 0, lat equals 2, 1 equals 3. So if you're thinking about index, from 0 to whatever it is, 50, the third one, the second one, or in this case the third one and the fourth one, right? 0-based indexing, and time equals 0. That's going to give you back this one point. All right, I'm going to skip over this 1.5 section. You can look at this later. Time here. It's down here so I don't spill it on my keyboard. Done that before. Okay, so we're not going to cover broadcasting. We're not going to cover all the stuff here. You can go back and look at that, of course, and go through that at your leisure. We're going to skip down to this high-level computation, where there's a lot of really cool things that Xarray can do with your data. And one of the coolest things is, again, well, we just listed the data set by typing DS, okay? And you can do a group by. So in this case, we're grouping by time dot season. So season has a meaning that is grouping by anything that exists in December, January, February is going to get in one of these groups, and anything, the rest of these seasons. So it groups by, or it looks at time, and it groups the data into these different groups. So there's these 4 groups, but you haven't really done anything with these groups. And now we're just going to take the mean of this, okay? So the mean of these groups, and just in one simple, calculation here, like very clear what you're doing, you can take a seasonal mean over this data set, and we get back, these 4 seasons on our grid. I mean, and you can see down here what these seasons are. And you may ask, like, what if I want to change the seasons, right? Like, what if I want to do bi-monthly, calculations? And for that, like somebody said earlier, I think Colin said earlier, like, I can never remember how to do anything Xarray. Me too. And so, this is where I think you're going to get an ML, coding it with ML or something later, right? But you can do like, let's see, do I have some? Oh yeah, write Python code to compute bi-monthly means using a custom group by an Xarray. And, and almost any of these tools will happily, give you back. So this is what I typed, right? Write Python code to compute bi-monthly means using a custom group by an Xarray. And here's what comes back. You create a sample data set. This is just some, example of creating a data set. So they created this data array, and then they defined these bi-monthly, bins by using a pandas date range with frequency of 2 months. And then they used data group by bins, along the time dimension with these bins to get the monthly means. And so, like, that would take a while to like dig through the Xarray documentation to try to figure that out, right? But thanks to Copilot and all the other tools like it, so you don't have to remember as much anymore. But you do have to remember, you have to know enough to be able to say, like, maybe you don't need, I don't know, maybe you don't need a custom group by whatever. Who knows how smart AI is, when the time when you use it. But anyway, usually you have to use enough, know enough the lingo to at least ask, to have it come back with the thing that you want, right? And they, usually they work. A lot of times they, almost work. Sometimes it's garbage, but it's still going to be faster probably than digging around in all the documentation. All right, I just wanted to show you that really quickly. So this is, I already did this. Oh, I see. Seasons are out of order. Okay, so we can use select to change the order of the seasons, and then we can plot them out with Matplotlib. And this is all I want to show you from Xarray in 45 minutes. So we're going to shift gears to, there's a lot of stuff. Actually, before we leave this, I just want to say that there's Xarray is like this core package, right? But there's tons of packages out there that are like compatible with Xarray, like these utilities, like there's X histogram, there's X climb, something for like comparing like models to data, and there's XVec for representing like polygons in Xarray in data sets. And I mean, there's a huge list. I think at the end of this, yeah, so there's, okay. Well, this is talking about different, okay, I have to talk about that. Some of these different packages. Okay, yeah, down at the bottom here. This is just a few of them, actually. We should probably submit a pull request and add some more. Yeah, there's a read gritter. This is for handling, read Xarray is for handling raster data. So if you're reading like optimized geotips or other kinds of image data into Xarray. You're using Rio Xarray, yeah, XClim I mentioned, climate stuff. Anyway, there's just a bunch, and actually this ecosystem page is probably the place to look. Actually, let's just click there and check it out real quick. So here, here's a bunch, a much longer list of all these Xarray packages. The main point is just that there's this huge ecosystem around Xarray. So it pays for you to learn Xarray. And if you think, oh man, I wonder if I could do this with Xarray. If you can't do it with Xarray, there's probably somebody who's made a package that lets you do it with Xarray. So before you start trying to code your own thing, do your due diligence and look around at all these different packages that are out there that work with Xarray. So, so now this is a notebook that I made, as opposed to the other one, which somebody else made. And okay, so this was when I think I mentioned I was at USGS. Just before I left USGS, I did this notebook. The problem we had a whole bunch of model output from the ROMS ocean model. And this was a forecast archive. So we had hundreds, actually we had thousands of NetCDF files that have been produced over a series of years. We made a request to the public dataset program at Amazon to see if they would be interested in hosting this data on their public data arc, for free to the public. And surprisingly, not that many people make the requests. And if they think it's somewhat useful, they'll usually say yes. In fact, I'm not sure I've ever heard of them saying no. Well, they probably would if it was really some ridiculous pet project or something. But in this case, they said yes. And so we were able to just upload all our NetCDF files to the cloud, and it's hosted and paid for by Amazon. And then people can access it for free with no egress fees or anything. So it's a really nice way to distribute data sets that are of common value. So Amazon's paying for the storage, and you don't pay as a user to access the data. Okay, so the data is out there in this object storage, and we wrote a notebook to show how to use it. So if you Googled CO, this is the CO coupled ocean atmosphere wave and sediment transport model. That's why it's called funny. And this model is very typical of the kind of curvilinear model output you see all over the place. And we wanted to, this is an example notebook that shows people, okay, you've got all these data, all these NetCDF files and object storage. How do we access this? And this is a notebook that goes along with the data set. If you Google COAWST and AWS, you'll land on the repo, or you'll land on a page that this notebook is from, and it'll describe a little bit more about how these, what we did to actually manipulate the data to be, more cloud optimized. I'm not going to go into that whole thing, but there are some things that you want to be aware of if you want to make your data more friendly to people using it on the cloud. So anyway, we're importing a bunch of packages. In this case, we're opening up the data set not directly as a, we're not going directly to these NetCDF files. We've actually represented the NetCDF files in an intake catalog. Intake is another package that plays with this ecosystem. Reason we have this so this is, instead of having all the parameters that you normally need to include in your Python code to load a data set, those are put in a catalog so that the user can then just open the data set. And if the data moves from Amazon to some other place, the user can still just go to you modify the catalog as a data provider, and then they can just still use the notebook, right? They don't care necessarily where the data is coming from. They just don't want to have their notebooks broken when you move the data. So this is a nice way to handle that. I'm not going to go into the details of this. So a lot of this is just be aware that these things exist. So in this case, we can list all the data sets in this catalog, and there's one because it's a very small catalog, just one data set. But we can see what the, actually I'm not going to go into the details there. We're going to just say, we can say we have this data set, we have this catalog, and we select a data set, and we can just say to Dask in this case. And remember I mentioned Dask in the beginning, and we can get back this this DS object, and again we can just type DS, see the data set, and comes back. You know, it shows us in this case, we have 112,000 time steps. So this is no longer, you know, a 7 megabyte like sample net.cdf file. This thing is huge, and in fact, it's got 188 data variables, you know, all sorts of different variables. Okay, and if we want to see like how big this is, it's not ds size, it's dsn bytes. And so I'm going to divide it by 1 times e to the 12th. Does anybody know what that is? That's that is terabyte. So it's 47 terabytes. So this is a lot of data sitting out there. So this is where Xarray really, you know, also shines. It's great with small data, and it's awesome with big data. So in this case, same stuff we did before. Pick a variable, take a look. Now we have a data array. We're going to look at this significant wave height variable, h wave. And again, now if we load it with this with Dask, so this is now backed by Dask arrays. We're not going to get into the whole Dask thing exactly, but just know that like Dask is like can then work with chunks of data. So each of your chunks can be loaded in parallel and processed in parallel. And if we click on like one of these, actually, it already shows us right here. If we just type the variable name, we get this nice little view. If it's in Dask, we get this view of data, where we can see this one data array is 126 gigabytes, but it's got chunks of 25 megabytes that are 168 in time and 168 in latitude, 224 in longitude, and or IJ. And these 24 megabyte chunks can be loaded. You know, you can just load it with it'll use the CPUs like just locally to load data in 24 megabytes at a time, chunking along. So like this is a small amount of memory we have on this machine, right? But we can work on this big data set by just letting it go through these chunks, chunk, and loading 24 megabytes, like taking the mean or whatever, and that would be fine, right? That would be one way to process big data, is just using, you know, processing the data in chunks using your local CPUs. Yeah.
Sorry, we can choose the chunk size, yes?
So that's a good question. So chunking is probably like a whole other, you know, tutorial, but you can specify chunks when you open up the data set, and it will tell Dask to load data in that chunk size, but the underlying data set also has a chunk size. And so you want if you tell Dask, it can be very convenient to tell Dask, like the chunks are very small in the native files, it's often very handy and faster to tell Dask, don't read just, so let's say it's like somebody chunked the data and it's like 50 in Latin long and 1 in time. Those are really tiny chunks. And you can tell Dask like chunks, when you open the data set, you can say chunks time equals 100. And each task will then load 100 of those little chunks and represent them as one chunk in memory. And so that can be much more efficient if the chunks, but always do a multiple of the underlying chunk size in the data. So you need to go look and see, like in encoding, I use encoding all the time. So like DA, you know, H wave dot encoding. This. Oh, great. Okay. Because what did I do? I did, oh, DA, yeah. DS, right? DS H wave encoding. And I can see that these chunks, the underlying chunks again, you know, 168 by 168 by 224. So if I told Dask to open and specify chunks, if I just say chunks equal, I can say chunks equals left squiggly brace, you know, right squiggly brace, and it would just load the native chunks. But I could also say like ocean time equals, and I would typically say like 168 times 10. So that it's kind of clear that I know what the underlying chunk size is, and I'm going to multiply it by 10 to tell Dask to read more chunks at once. Does that make sense?
Yes. Okay.
Okay. So as we saw earlier, you can use the CF conventions to uniquely determine like what variables are actually longitude, latitude, and time, as long as the data is CF compliant. So somebody might have actually called the variable lon2 or whatever, something different than, like people call longitude all sorts of things, but if you say not CF longitude, in this case, see, I print out the names that it found, and actually longitude was called lon_rho, this variable, and lat_rho was latitude, and ocean time was time. But I don't have to use these names now because I used the CF. I used CF to find the names, the weird names that were associated with standard names that are given here. All right, so then we're going to use what we saw before to just like load a particular time step, right? And because I use CF, I can say capital T instead of like whatever, ocean time or time. I can say capital T equals the time, method equals nearest, load that, and in 5 seconds, I've extracted this data. So I said .load on the end, and that loads the data into memory. 5 seconds, I've extracted this slice from this 47 terabyte data set sitting out on Amazon, right? Directly out of object storage. So there's no OpenDAP, there's no other data services involved, which makes it very robust. Like as we were mentioning earlier, like sometimes you do these tests and like, oops, somebody's RDAP server or some, usually not RDAP. RDAP's very stable, but thread servers often go down or whatever, and then your workflow's not going to work. But with loading data directly out of object storage, it's super reliable.
Our RDAP servers having up right now.
Yeah. So, I mean, a lot of these data services we've developed are awesome for their functionality, but in terms of like being like, production grade, robust, like people were rebooting them at midnight and stuff like that. Like, okay, you don't do that here in these workflows. Anyway, and then I'm going to show you this HV plot. Instead of, we could say .plot here. Maybe we should just do that. Actually, let's do that. We're going to add a DA2D.plot. Let's just see what we get. And yeah, sure enough, we get a quad mesh, but we can make that look a little better, right? By telling it what longitude and latitude is. You can there's Florida. Looks kind of funny. But we can do .hv plot if we've done import HV plot. And this is super cool because in one, we can do things like we can tell its geographic coordinates here. We can tell it to use OpenStreetMap tiling. We can tell it the color map. Okay, we can do that in the regular plotting as well. But in one like line, you get something that looks almost like some interactive web app. Like you can hover and see the values. Like you can turn off the hover tool over here. These are tools from Bokeh, which is underlying this stuff. And the coolest thing though is like, okay, I got this plot, but what's going on like in the Gulf of Mexico? I can't tell because there's this big storm, Hurricane Sandy, going on up here. Okay, so but I can just go and I can click this like little box zoom tool, and I can go in here and zoom, and it will rescale and just deliver the pixels back to the browser for that region. And so now you have like this totally interactive scale, this tool where you can go along and see, what's going on in your model or whatever, or your remote sensing data at the full dynamic range by just zooming in and out. And this is super handy for like triangle mesh, like at certain models of where you go from the whole Atlantic Ocean down to some levee, and with this tool, you can just go zooming, and it just keeps rasterizing. It'll never blow out your browser because it's just delivering the pixels. You're like 400 by 400 pixels. It's rendering on the back end, so it's super cool.
I have a question.
Yeah.
Could you like publish that map anywhere, or would it like stay with you?
So you can, you can export these as pings, but you can't do much better than that. Like, because it is raster data. So, yes, you can capture the output. And actually, you can switch the back end from being this interactive bokeh thing, you can say backend equals matplotlib, and then like have a regular matplotlib plot. Right? Now I'm going to.
This allows you can actually export them as HTML. So you'll be able to zoom in and zoom out. You will not get the highest resolution because there is no Python running in the background, but you can still zoom in.
Yeah.
Pretty good, actually.
Yeah, that's actually pretty cool. So like if like in this case, if you really want to show people like, well, actually, yeah, the ones where it's rasterizing in real time, that maybe not the best example. But if yeah, you have some example where you're like going through a time series or something like that, and you want to be able to watch, I'll show you in a second. Actually, we could even do that. No, we don't have time.
Streamlit or panel, you can build a interactive server that's running with your data.
Yeah.
And HV plot.
Yeah, that's another cool thing. Just being able to like move out of the, you could maybe figure out how to share your notebook with somebody, but then they need the whole environment and everything. And sometimes you just want to have some like, the boss or headquarters or whatever, the emergency response people or whatever, they don't want to run a notebook. But you can just take this, your whole notebook that produces some cool thing with HV plot, and you say panel serve in your notebook. And it just, then you can just send people to a URL where they just see the output and they can interact with it, but they don't see any of the Python code. I think it just said exactly what you said. Anyway, so now I want to just show how you use a cluster with this kind of situation. And again, we're just like blowing through all this stuff, but just to make you aware of it and show you how cool some of this stuff is. So in this case, we picked a particular location in the Gulf of Maine. Okay, and I don't really want to go into this exactly, but we're using this tree to figure out what IJ index it is, because this is a two-dimensional latitude and longitude array, so we can't just say we can't use Xarray to just say nearest point to this, although in the near future, I think we will be able to. But anyway, this is just some code to figure out what data point to load. Okay, so I'm not going to dwell on that. But I'm picking in this case a particular time period of October 2012, and I haven't done .load at the end because I wanted to see how much data I'm talking about loading. And so in this case, I'm loading 744 times at a single point. And it's tiny, and it's going to load to get this data. It's going to have to load 5 chunks of data. Well, 5 chunks of 24 megabytes. That's not that much. Like we don't need some fancy cluster to do that. So we can just do that, load the data, and 1001, 1000. Okay, 2.4 seconds to load those 5 chunks of data. Okay, so we've got this 1 month of time series data. And again, we've got these nice little HV plot tools where we can zoom in and check out like this big storm event, which was Hurricane Sandy at this point in the Gulf of Maine, right? But now I want to show you like really kind of cool thing you can do with big data. So what if we wanted to load the whole thing? Like, what if we wanted, instead of just 1 month, what if we wanted all 112,000 points? Well, we have to load 168 chunks of data. Yeah, we could do that and wait around, or we can actually parallelize this by spinning up a Dask cluster. So underneath Xarray is Dask if you want to use Dask, and it can use all these different types of clusters. So it can use a local cluster, which is just the data like the CPUs on your local system. So maybe we have 2 here, and we could look, but I don't have time. So I have this little, logic in here, like if you could try this out on your own, like you could say, I want a local cluster, and that would use your local CPUs, but I need to execute this line where I say, I want cluster type coiled. Oh, whoops, okay. So anyway, I executed this cell that said if it's cluster type coiled, import coiled, I'm gonna create this coiled cluster, and I've got all these options. You actually don't need all these options, but I put them in here just to kind of show you like the range of things you can do. You can spin up a cluster in a particular region, in this case on Amazon. I can say I want to use ARM processors, which use less energy, so I'm going to be green and maybe save myself some money. I'm going to specify like what these like instance types are. Just now, you typically wouldn't do this; you just let it pick instance types. But then if you go back and you find out that these instance types were hardly being used, you could go for smaller, cheaper ones. I'm going to ask for 30 workers. I'm going to wait. I don't want to wait for all the workers to show up. I'm going to use like spot pricing, which makes it super cheap. Like if there's free cycles available, it'll use those. I've saved I'm gonna name this cluster Coast. I've saved a Python environment called ESIP and GeoArm by doing like a coiled create an environment, like with a YML file, just like you create a normal environment. And I'm working in this particular workspace. We can create groups in a certain account. So this is all running thanks to the Earth Science Information Partners who have gotten a generous grant from Amazon to help people in the geo communities explore cloud native workflows. And I'm going to say leave this cluster running for 180 seconds in case I end up wanting to use it again before it just shuts it down. And so then it said, get the client, and it's waiting for the workers. Actually, no, all the workers are here already. So it tells me, yeah, they've all arrived. It complains a little bit about some minor version differences between the Python environment running here in the hub and that I have already saved on my coiled account. But let's just get to the good stuff. Let's run this thing. So actually, this is these are other types of clusters that we're not using. Actually, you can, once you've created a cluster, no matter how you create it, you can always type, oops, oh, did I just do it again? Oh yeah, okay. Oops. If you've already got a cluster, name something, you execute it again, it'll just use that existing cluster. I meant to execute this cell, that you can execute with any kind of cluster, and I can see that I have these 30 workers with 60 threads and 40 gigs of RAM. There's a dashboard link where I can see what's going on. Now I'm going to load the whole thing. Okay, so I'm going to load the whole thing. That's a big computation. And we can click this dashboard link to see what's actually happening on all these different, each of these horizontal lines is one of those workers, and it's reading, each one of those is reading chunks of data. So they're reading chunks of data in parallel, and it's falling out for some reason. Why is it? Or maybe this didn't update fast enough. Ooh, whoa. Okay. Future canceled error. This coil provides a really good like accounting of what's going on. So like you can have a team, you can have people on the team. You can set their limits so that they don't blow out your cloud account. You can set it on individuals. You can set it on a group. You can see how much exactly everything costs. I've actually never seen it. Just not like do what it did just a second ago. Okay, we have 5 minutes left. Hopefully this will. I mean, I've been using this all the time, so but it's the curse of the demo, I guess. Let's see. So. It's a little bit of an annoying thing in the notebook. It keeps skipping down to the bottom. But now you can, okay, so you can see what's being requested here. The scheduler is still starting. Okay, so provisioning 0. Okay, 21 are ready. It's booting 2. So it creates these workers on the fly on Amazon, and then it then they have to get the software environment. Okay, so now it's done. So let's see here. Well, it does seem like it is losing somehow the connection to the workers. I wonder if maybe the internet is like sufficient to.
Or I'm wondering if the firewall is seeing that connection type that it hasn't seen much of before.
Maybe the firewall, yeah. Because
No, that would be that connection is coming from the IPC cluster, not Signell.
Yeah, because I was running. I mean, I ran this morning sitting here, so I think okay. Well, this time it worked, but it worked so quickly that I didn't have time to click the dashboard. So no, okay. Oh, so this is another calculator. Okay, so further down the notebook, once you've got the cluster established, so I selected the data, and it took 16 seconds to load all that data because I had all these workers working. And so we can plot the entire 112,000, whatever it was, points here in just 16 seconds, right? We extracted an entire time series from this 47 terabyte data set by using a bunch of workers working in parallel. And, now we can, we can zoom in on this thing like we can zoom in like we did before, and just like, hey, that data from 2012, we're looking at, here it is kind of, right in here, right? And then, in this notebook, we, again, with the same cluster, we're actually doing the mean over like an entire year here. And it took 5 seconds because all those workers were already spun up. And so they're all loading data in parallel and then just delivering it back, behind the scenes to your command here. And then at the end, so we took the mean over an entire year of this wave height data. In this case, we actually saw some kind of cool result that we didn't expect, where, we were just trying to take the mean and see what the mean looked like, but we saw this local increase in the wave height in the Gulf Stream. Normally you'd think, oh yeah, okay, the waves get bigger offshore, but in this case they get bigger in the Gulf Stream, and then they get smaller when you're out of the Gulf Stream. And this is because this is a coupled model. It's got, the waves are coupled to the waves and the wind are coupled, and so the wind that the sea feels in the Gulf Stream is different because of the strong currents, the ocean currents. So anyway, except for that weird area that we don't understand, hopefully that was impressive. And there's a lot. I use this stuff all the time. There's really no way you can work with climate data other than this kind of approach, because there's just so much climate data. So if you work with, I work with a lot of organizations that want to ask specific questions about, how climate is going to impact the things they care about, and they always want to go and grab all this climate model output and just, crunch it all down to figure out what the thing is that they care about. And this is exactly the way to do it. There's other ways to spin up clusters. The coiled issue, I don't know what that was, but the other good thing about coiled is all the best people in Dask, or not all of them, but a lot of really smart people in Dask work for coiled. And if we can go, actually one thing we can go do is see how much that cost. So if we go to the dashboard, we can see that the cost of doing that was about 3 cents. So using coiled, even though they're a commercial company, you actually end up paying them 5 cents on the dollar if you use more than a certain amount per month. I have found that it actually saves me a lot of money, because I can do things like use cheaper instances and use ones that aren't being, and all that stuff that would be really hard for me to figure out on my own. Plus, I get really great support on Dask issues from the coiled team, because they're all Dask people, and I'm like a Dask customer. In fact, I've never given, ESIP has never given coiled any money, actually, because they give you 10,000 free credits a month. So you're going to pay for your Amazon or Google or Azure, compute, but you only pay coiled if you use more than a certain amount per month, which currently only I think the finance people are doing. So kind of the finance community is kind of financing us in a way, which I think is kind of cool. Anyway, all right, sorry, out of time, but.